In this section of Chapter 2, we will discuss histograms. A histogram is a graphical display of data using bars of different heights. While a frequency distribution is a useful tool for summarizing data and investigating the distribution of the data, an even better tool is a histogram. A histogram is a graph that makes it easier to interpret the data than it is with a table of numbers. Histograms are a type of bar graph that allows us a way to visually display counts of the data. A bar graph charts actual counts against categories. The height of the bar indicates the number of items in that category. A histogram displays the same categorical variables in bins or classes. A histogram is a graph consisting of bars of equal width drawn adjacent to each other, unless there are gaps in the data. The horizontal scale, or the x-axis, represents the classes of the quantitative data values, and the vertical scale, or the y-axis, represents the frequencies. The height of the bar corresponds to the frequencies of the values. A histogram is the most commonly used graph to show frequency distributions. A histogram can be used when the data are numerical, when you want to see the shape of the data's distribution, especially when determining whether the output of a process is distributed approximately normally, or if you wish to communicate the distribution of data quickly and easily to others. Histograms visually display the shape of the distribution of the data. They also show the location of the center of the data. Histograms also show you the spread of the data, and it also helps you to identify any outliers. With a histogram, class frequencies are used for the vertical axis. And the horizontal axis, it is common to use the class boundaries or the class midpoints. However, there is no universal agreement on which value should be used for the bar's location on the horizontal axis. Recall that the vertical axis is the axis that goes up and down. This is sometimes called the y-axis. And the horizontal axis is the axis that goes left to right. This is sometimes called the x-axis. Recall that the frequency distribution of McDonald's drive-through lunch service times. We can use a histogram to display the distribution graphically. In this histogram, you can see that the boundaries of each bar is the class boundary from the distribution table, and these are plotted against the horizontal axis. The vertical axis, or the y-axis, displays the frequency of each of those classes. A relative frequency histogram will have the same shape and horizontal scale of a histogram, but the vertical scale is the relative frequencies, or the percentages, of those classes. The objective of a histogram is to get an understanding of the characteristics of your data. We can explore the data analyzing the histogram to see what we can learn about the CVDOT. CVDOT stands for the center, which is a representation of the values that indicate where the middle of the data set is located. The variation, which is a measure of the amount of the spread of the data values. The distribution, which is the nature or shape of the spread of the data over the range of values, such as a bell-shaped distribution. The outliers, these are sample values that lie far away from the majority of all the other sample values. Or time, any changes in the characteristics that happen with the data over a period of time. Let's consider 4 of the more common shapes of histograms. The first is the bell-shaped distribution. This is also known as the normal distribution. This is a distribution that occurs naturally in many situations. For example, the Bell distribution is seen in tests like the SAT, ACT, or GRE scores, where the bulk of the students will have scores that average like in the middle with like a C, while the number of students with a score of a B or a D will be a little smaller. And even smaller will be the number of students who score an A or an F. This creates a distribution that resembles a bell, hence its nickname. The Bell distribution is symmetrical, where about half of the data will fall below the left of the center, or the mean, and half will fall above it. Another common distribution is the uniform distribution. The uniform distribution is sometimes referred to as the rectangle distribution. In a uniform distribution, the different possible values occur with approximately the same frequency, so that the heights of the bar are approximately uniform. A skewed right distribution is also known as a positively skewed distribution. These distributions have a long tail on the right side of the histogram, and the peak of the histogram tends to veer over to the left. Also, the mean of the distribution tends to be to the right of the peak. Annual income of adult Americans is an example of a distribution of a population that is positively skewed. And finally, the skewed left distribution is also known as the negatively skewed distribution. These distributions have a long tail to the left side of the histogram, and the peak of the histogram tends to veer to the right. Also, the mean of the distribution tends to be to the left of the peak. An example of a left skewed distribution would be a population of the lifespans of humans. Note, a distribution is skewed when the distribution is not symmetrical and one side of the distribution extends more to one side than the other. This is an example of a distribution that is roughly bell-shaped. It is roughly symmetrical and has a single peak, and it resembles the shape of a bell. Many statistical methods require that the sample come from a population that has an approximate normal distribution, and we can use a histogram to judge whether that requirement is satisfied. We can use normal quantile plots to help assess the normality of a distribution. A normal quantile plot is a tool that we can use to help us assess if a data set may have come from a normally distributed population. The normal quantile plot is only a visual check and is somewhat subjective, so it's not an airtight proof, but it does allow us to see at a glance if our assumption is reasonable. A population distribution may be from a normal distribution if both of the following conditions exist. First, that the pattern of the points in the normal quantile plot is reasonably close to a straight line. And second, that the points do not show any systematic pattern other than that straight line pattern. On the other hand, a population distribution is not a normal distribution if either of the following two conditions exist. First, that the points on the plot do not lie reasonably close to the straight line pattern. And second, the points show some sort of systemic pattern that does not include the straight line. Let's look at some examples using the normal quantile plot. In this example, we see that the majority of the data points are positioned reasonably close around the green line. And other than a straight line pattern, there appears to be no other obvious pattern to the data points. This plot would give us some support to assume that our data come from a normal distribution. In this example, we see that most of the data points do not lie close to the green straight line, so we would be safe to assume that these data do not come from a normal distribution. And finally, in this example, you can see that while the data points are reasonably close around that green straight line, let's check to see if there's another systemic pattern. As you can see, about half of the data points hover just above the green line, and about half the data points hover just below the green line. This appears to be another pattern. This violates the second condition of the normal quantile plot, and so we would conclude that this distribution is not a normal distribution. This concludes Chapter 2, Section 2. Please move on to Chapter 2, Section 3, Graphs that Enlighten and Graphs that Deceive.